Hi, this is Professor Fernandez. We're working on class notes B in lesson 9. So this example asks us determine whether or not the systems of equations below have unique solutions. Okay, and what I'm trying to do here is reference the result that we got in the previous video and the previous example. So I'm just going to scroll back up to remind you what that was. Here it is, example 9.1. We had shown in the previous video that if I consider a system of two equations and two unknowns, as long as AD minus BC is non-zero, the system has a unique solution, okay? And it's given by that x value, that y value. And in the previous video, I kept calling this by its long form name, AD minus BC, AD minus BC. But now that we are talking a little bit further down the notes, we have given this a name, so I'm just going to scroll down. So this AD minus BC quantity for a 2x2 system, AD minus BC, is called the determinant of a 2x2 matrix. All right, so now that we have those two pieces of information, we can go back down here to the example and start solving that. So determine if the systems of equation below have a unique solution. First thing I'm going to do is I'm going to put them in matrix form. So I'm going to say coefficient matrix here, 1, -2, 2, -1, 1, -2, 2, -1. AX equals, and then right-hand side here, so 2, 1. Great, and I'll do them at the same time because this determination is going to be fairly simple based on what we've done now. So coefficient matrix here, 2, 2, first row, and then -3, 3, second row. And then right-hand side is 9, and then -4. Great, so based again off of the nomenclature and all of the work we did in the previous example, this is the coefficient matrix A here. This is the coefficient matrix A here. And all we got to do now is calculate this quantity AD minus BC, which is the determinant of this matrix. Okay, and as I show here, when you're calculating the determinant of a 2x2 matrix, it is the product of the diagonal entries minus the product, let me keep it in the same color. It is the product of the diagonal entries that gives you AD minus the product of the off diagonal entries that gives you BC. Okay, so we're going to do that down here. So for our matrix A on this side, okay, let's do that determinant. So determinant of, trying to get the colors right, 1, -2, 2, -1 equals product of the diagonals, so that's -1, minus product of the off diagonals, so that's -4. Okay, so we have -1 plus 4 equals 3. Excuse me. So that is non-zero. Therefore, by example 9.1, this system has a unique solution. Okay, great. And then I'm going to go over and do the same thing over here. So similar idea, the A matrix over here is 2, 2, -3, 3. I'm going to calculate its determinant. So product of the diagonals, 3 times 2, 6, minus product of the off diagonals. -3 times 2 is -6. So you can see what is happening here. I get 6 plus 6 equals 12. Excuse me. So that is, again, not equal to 0. Therefore, by example 9.1, this system also has a unique solution. Okay, so we have arrived at a unique solution for both of these systems. And because I have a little bit of space down here, let me just add a C, part C, if you will, and illustrate what would happen if I change the matrix up here from 2, 2, -3, -3 to just 2, 2, 3, 3. Now you can maybe see what's going to happen because these matrix would row reduce to 1, 1, 1, 1, and then that would row reduce to 1, 1, 0, 0, which is a matrix we've met before and yielded infinitely many solutions. So how do I see that with this determinant? Well, I would take the determinant of 2, 2, 3, 3, and then do the same process. I would multiply the diagonals to get 6, and then minus multiply the off diagonals to also get 6. Okay, and that would give me 0. And again, I go back to the example 9.1, where in the second part we saw that if this quantity AD minus BC for these 2x2 systems, which we now know as the determinant, is 0, then the system would have infinitely many solutions or no solutions, right? We need to do some additional analysis to distinguish those cases. Okay, so that's the end of the video.